Imagine we took this box here. So imagine it's sort of an empty box with no top or no lid on it, and we dropped it into a pool of water. And in this scenario, imagine the water's going over the sides and it's sort of filling up this box. So we're going to run through a couple questions here dealing with the hydrostatic force on various sides. First of all, we're going to look at the hydrostatic force on the bottom of this box. And secondly, and we're going to look at the more complicated question of what is the hydrostatic force exerted on one of the sides of the box, which is a little bit less intuitive and requires a little bit of calculus. So first question will address the force on the bottom of the box. Now we can just look at this and just consider this as basically all the weight of the water that's sitting on top of the box is going to be exerting that force down on the top of the box. So we could really, it's not too bad. We just got to find the volume of the water on top of the box and then multiply that by the density and by the gravitational constant. And that's going to give us that force that's exerted on the bottom of the box. So this force here is going to be the volume of all that water sitting on top of it times rho times g. Where our volume we could easily find by multiplying these three dimensions here, 5 times 6 times 2 for 60 meters cubed. Rho in metric units is 1,000 kilogram per meter cubed, and g, the gravitational constant, is 9.8 meters per second squared. So to find the force, you just multiply all these together, and if you just kind of keep those units the same and multiply those, you get 588,000 kilogram meters per second squared, which we can convert a bit knowing that 1 Newton is equal to 1 kilogram meter per second squared. So we can change those units a bit and call this final answer 588,000 newtons. So that's how we find the force on the bottom of the box. There's sort of a different way we could look at it. We could look at the pressure on the bottom of the box from the water, and then we could multiply that by the area of the bottom of the box, where pressure is defined as the force per area. So essentially, there's pressure at any given point on this on the bottom of the box. It's given in newtons per meter squared, or a Pascal. So if we took our last equation, we could say the pressure of the plate is the force of the plate, like we just calculated, divided by the area of the plate. So the force on that plate we just calculated was the volume times the density times g, and then the area of the plate is that 5 and the 6 again. And you notice that we just multiply by the 5 and 6 to get the force of the plate. Now we're going to divide by it to get the pressure. So imagine we just cross those out, and it turns out that the pressure on the bottom of the plate is just going to be rho times g times h, which in this case is 2 because it's 2 meters deep. So if we kept the units right here, we just say that's 1,000 times 9.8 times 2, and we do the Newton conversion, and we get this is equal to 19,600 Newton per meter squared, or pascals. Now, before we move on with this, just consider intuitively what this is saying. It's saying that the pressure is not a function of that area, that horizontal area, but it's just a function of that what we're calling h here. Now, typically you think of that as depth. It's often referred to as d. You can call it whatever you want. I'm going to call it h here because I don't want a dd when we end up integrating this. So just to be consistent, you may see it d otherwise. You can use whatever you want, but for this case, I'm just going to go with h. And imagine that as you go down in this pool, say you were to dive into this pool, you would feel the pressure increasing as you go down, right? So what we're seeing here is that pressure is a function of your depth as you go down deeper into the pool. So you probably all experienced that if you've dove in a pool before. One other way you might think of it conceptually is, say we had this pool, or maybe a bucket like is shown here, and we poked holes of equal radius at different depths in the box. You can imagine that the hole in the bottom, there's going to be more pressure down there, so that water is going to shoot out faster with a higher pressure, whereas the hole on the top isn't going to have as much pressure, so that water's not going to shoot out as far. So it's kind of an intuitive understanding that hopefully isn't too hard to grasp. So another way we could have calculated this problem is we could have just said that we could have found that pressure on the bottom of the plate and multiplied that by the area of the plate. So we could have said the force on the plate is the pressure on the plate times the area of the plate, and we know the pressure is just rho GH, which we calculated earlier. We know the area of the plate is just 5 times 6, those dimensions on the bottom, and we end up with 588,000 newtons, which was the same thing we had gotten earlier when we just found the weight of the water. So this is just another way that we could have found that pressure on the plate. So before we move on to pressure on the side, quick question. So which of these is bigger, P pressure 1 on the left plate or pressure 2 on the right plate? Well, if you guessed that they're the same, then you're correct because pressure is only a function of depth here, and they're both 2 meters deep, so that pressure on P1 is going to be the same as P2 because that area of the plate doesn't really matter. That's kind of taken out of the equation for pressure. All right, so moving on, let's discuss the force exerted on the side of the plate. Now, this is a little bit more difficult to fully grasp because there's really no we can't think of it as like a water sitting on top of it because there's really no water sitting on top of this on the side of the plate. It's um the force is coming in from the side and there's water there, but nothing's like sitting on top of it, so it's not quite the same. However, something to note about water pressure is that it's actually equal in all directions. So the same force that's exerted downwards at any given point in this water is also exerted to the side or upwards at that given point. So you can imagine if you dove in here and this is your head, you're going to feel essentially equal pressure coming in on the side of your head as you are on the top of your head. So that same weight of that column of water that's sitting above your head that's pushing down on your head is also pushing in on the side of your ears. But if you wanted to be actually a little bit more precise, you would say that you're feeling a little bit more pressure on your ears than the top of your head because your ears would, in this case, would be like a little bit deeper than the top of your head. Certainly nothing that you would really be able to tell a difference with, but there would be a difference there. So understanding that pressure is equal in all directions, that's going to help us calculate that force on the side of this plate here, or on the side of the box, if you will. So one way we could do this, a really basic way, we just, well, actually, before we move on to that, quick question. So which is greater, P sub 1 here, the pressure at the top of this, at the side of the plate, or P sub 2, pressure a little bit lower? Hopefully you'd answer P sub 2 is greater than P sub 1 because it's deeper. So deeper, there's going to be more pressure exerted on the bottom of the side of the box than on the top of the side of the box because it's deeper. So back to trying to find this total force on the side of the box. We could do a really basic estimate here and just say that the force on the side of the box is equal to P times the area of the side, and we could just assume a constant P. Of course, as we just saw, P1 was not equal to P2, so it's not a constant force on the side of the plate. But we could just pick a pressure there and try and get an estimate. So we could use P pressure is equal to rho times G times H, and for this case, we'll just say H is 2. So we're just looking at assume that the pressure across the whole plate is the same as the pressure exerted on the bottom of it. In that case, we're going to end up with 19,600 Newton per meter squared. And then we find the area of the side, which in this case is just that 2 times 6. And that's going to give us 235,200 newtons. And we're just going to go ahead and call this our n equals 1 estimate, where n equals 1 is the total number of sections that we divided it into. So we didn't really divide it. We just left it as one section. And as you can imagine, this is quite an overestimate because we assume that the pressure across the whole side was at the actual maximum pressure, which was the pressure at the bottom. So how can we improve on this estimate? Well, we could separate this into two different forces to make this a little bit more accurate. And so we'll call this our n equals 2 estimate, where we're just looking at two different forces, and we'll call the total force on the side equal to F1 plus F2. So we're looking at the force, F1 being the force on the top half of that side, and F2 being the force on the bottom half of it. So to solve for F1 first, we could just identify pressure sub 1 and area sub 1, where pressure sub 1 is going to be rho times g times h sub 1, where the h's are defined over here on the right of the box. So h sub 1 in this case, we'll just call that 1 meter, whereas h sub 2 will be the bottom at 2 meters. So we're just essentially going to assume the pressure that for the top half of this section, we're just going to assume the pressure at the bottom at h1 equals 1 meter. So plugging in some numbers here, we end up with the pressure is equal to 9,800 newtons per meter squared. And that area is going to be 6 times 1. So that's the area of that upper section. Now notice that with this we can calculate F, which is 9,800 times 6, which is 58,800 newtons. And notice that we were able to calculate the force on the side of the box without ever even considering that length, that 5 meters of the box. So it turns out that that 5 meters that you see there has no bearing on this question. I mean, it was important when we wanted the force on the bottom of the box, but when we're looking at the side, it doesn't, that length there doesn't factor in. So now that we've found F sub 1, we can go ahead and find F sub 2, which we find in a similar way. We're just looking at P sub 2 and A sub 2 here. And really the only difference here is we're assuming a different depth. So instead of H sub 1, we're assuming H sub 2. So we're assuming that that pressure exerted on that bottom section is equal to the pressure that's really at the bottom of it, where our depth is 2 meters. And this is going to give us 117,600 newtons per meter squared. Our area of that bottom section is going to be the same as the area in the top section because we divided these into equal sections, which is just going to be 6 meters squared. And finally, we can go ahead and find our force on the bottom section, which is 117,600 newtons, and then we can go ahead and plug these in to find our total force on the side is going to be F sub 1 plus F sub 2, which is going to give us 176,400 newtons. So we'll go ahead and put this on the bottom here as our n equals 2 estimate, where in this case n is referring to the number of sections we divided it into. Here we divide it into 2 sections, and we notice we get a little bit better of an estimate because we weren't assuming the 2 meter depth the whole time. Now we were kind of splitting it up so that the bottom, we were accounting for the fact that the top section doesn't see as big of a pressure on it. And so it's less of it's still an overestimate, but it's less of an overestimate now. And certainly an improvement on our estimate. So this is better, but how can we make this even better? Well, we could divide it up into more sections. And this is going to give us the more sections we divide into, the more accurate of a estimate this is going to give us. We're going to define things a little bit differently here. We're going to call that h at the top is 0, h at the bottom is 2, just to explicitly define those h values. And we're going to call this a sum. So the total amount of force on the side is going to be the sum of the force on all those different sections. So in this case, it looks like our capital N would be 4 because looks like we're kind of dividing up into 4 sections. But that's just sort of meant to represent a bunch of sections there. So our total force is just going to be the addition of the force on all those sections. So you can make this a little more precise by calling the force on in an individual section is just the pressure of that section times the area of that section. So the area of any given section this is actually going to be constant no matter what. It's not really dependent on n. It's just because our delta H is going to be the same, where delta H is shown here on the right. If we want to define it explicitly, it's going to be h bottom minus h top over n, capital N. And this will be, it's important to define this explicitly if we want to actually calculate this sum, which we'll do in a little bit. So that's our area of any given section we're looking at. Now that for the pressure, this is actually going to vary with n. It's going to be rho times g times h sub n, where h sub n is going to vary, and that's going to be the height at which we find the pressure. You can see over here, h sub n is identified as sort of the third height down, and it's going to be n times delta h, where in this case you could see that that's going to be, that value there is going to be equivalent to 3 times our delta h, where our delta h here looks like it's going to be 2 over 4, which is a half, so our h sub n, as it's shown here, looks like it'd be about 1.5 meters. So knowing a sub n and p sub n, we can just throw these back into our summation, and we get this. So this is going to be the total force. Now, if we plug this into Desmos, we can get some different values here, and we can actually ratchet up capital N as we like. So in this case, you can see that the equation I have in Desmos here, the summation, is a little bit more complicated than what we're showing on the left because we've just subbed in for h sub n and delta h according to how we define them below. In order for Desmos to do this, you've actually got to put in, you can't just leave h sub n and delta h. So we threw those, well, we were a little bit more specific here. And you can see that when we make capital N equal 1, that means we're just dividing it into one section, so we're not really dividing it at all. We get 235,200, which matches our initial N equals 1 estimate. So it looks like that checks out. Now if we crank that capital N up to 2, as if we're dividing it into two sections, we get 176,400 newtons, which you can see matches up with our N equals 2 estimate. So now we have a bit of a confidence in our summation, knowing that it matches those first two values that we found. It's always good to check these your programs here just to make sure that they're in line with what you find by other means. So it looks like we're on the right track. So it looks like this is a somewhat trustworthy summation, and it's giving me the appropriate force depending on how many sections I divide it into. And so now we can go ahead and ratchet that capital N up to 200,000. So this is the benefit of throwing this in Desmos, is now I can just get to ridiculously big N values, and it Desmos impressively cranks this number out pretty fast. And when you get up to 200,000, it starts to converge towards 117,600. In this case, there's a 0.6 on the end. So 117,600.6 newtons is our estimate. If we divided that area of the plate into 200,000 sections. So it's pretty good. Now we're getting to a pretty good estimate here, you think, right? 200,000 sections, we're getting somewhere. But we can do even better. What if we want an exact force on the side of the plate? So here we're going to make h continuous, whereas before we had it defined as h sub n. And we're going to find that exact force. So exact force on the side is going to be the limit as capital N approaches infinity of this summation that we found earlier. And the only difference here is I'm throwing a limit on there, so I'm saying as N approaches infinity. We got N pretty large last time with 200,000, but our exact value is going to be found when N approaches infinity. So we can now, based on the summation definition of the integral, we can actually change this into an integral. So we get that delta H transfers into the DH, that the middle part just transfers to the same thing, rho times G times H times 6, except for now that H sub n, which is a discrete H, becomes a continuous H. And we're integrating from the top to the bottom of that plate. So we can fill that in a little bit, so where the top and the bottom are 0 and 2 meters, and we can fill in our rho and our G, and we can go ahead and throw that outside and integrate this function, which isn't too bad. And crunching through the numbers, when h equals 0, we just get 0. So we just really have that first term. We just really evaluated at that first term. And we end up with 117,600 newtons, which is going to be our exact force on the side. And you notice this is a bit easier than doing an infinite sum. Calculating integral is this actually goes pretty fast, right? So we wanted if you understand how that summation works, it's simple now just to go straight to that integral and get your exact value without too much effort. So in summary, we looked at the hydrostatic force on a horizontal plate, or in this case, the bottom of the box. Then we looked at a few different ways to calculate the force on the side on a vertically oriented plate, which is a bit more complicated because that pressure is changing. And so we first looked at a really gross estimate where we just assumed the pressure was constant the whole time. We got 235,200. Then we divided it into two different sections, got a little bit better estimate, was a little bit less of an overestimate. Then we next put it into summation formula and divided it into 200,000, and we started getting closer to our exact value, which we finally calculated using calculus at 117,600 newtons.